Hey everyone, and welcome. So today we are diving into one of the most fascinating puzzles in modern artificial intelligence. Have you ever stopped to wonder why today's bleeding-edge AI models need just this absolutely staggering amount of data to get smart? Especially when you compare them to, well, us. Biological learners don't need to read the entire internet to learn how to speak. It's a fundamental mystery that researchers have been obsessed with solving. In this explainer, we're going to break down a really groundbreaking paper that mathematically proves how AI might finally bridge this efficiency gap. And the secret? It's all about changing what the AI actually pays attention to during its training.
Okay, just look at this number, 10 to the 13th to 10 to the 14th. We're talking up to 100 trillion. That massive, honestly kind of incomprehensible figure represents the number of raw tokens, like fragments of words or individual pixels, that state-of-the-art large language models are trained on just to achieve basic competence. It's literally an ocean of data.
Now, the contrast here is where things get really interesting. When we put that massive AI data diet side by side with the human child, the difference is jarring. A child hits adult-level fluency with about 5 orders of magnitude less data exposure. 5. They don't need 100 trillion words to understand how the world works. So the really crucial question we have to ask is, what are we doing right that our current AI models are doing wrong?
Here's our roadmap for decoding this today. We'll start with the AI data problem. Then, tokens versus latent concepts. Third, modeling hierarchical learning. Fourth, the efficiency breakthrough. And finally, towards human-like AI. Let's jump right in.
Section 1. The AI data problem. Let's look at this massive data gap.
Section 2. Tokens versus latent concepts. These are essentially two competing paradigms for how AI can learn.
So what is the actual difference between predicting raw data versus abstract concepts? Well, the working theory right now is that learning simply isn't efficient at the level of raw, surface-level tokens. When an AI tries to learn by predicting the exact next pixel in an image, or the exact next letter in a word, it just gets totally bogged down in the noise. Let's define what we mean by a latent. A latent representation is basically an abstract, higher-level concept. Think of it like this. A token is a single pixel on your screen, but a latent? That's the actual concept of a dog, or the underlying meaning of a sentence. Which one sounds easier to learn from? Identifying the general concept of a dog, or obsessing over the exact color value of one tiny pixel on its ear?
And actually, this brilliantly mirrors a concept from neuroscience. In the human brain, there's a theory called predictive coding. It suggests that our cortex isn't just constantly trying to predict the raw, granular sensory inputs hitting our eyes and ears. Instead, the brain is constantly trying to predict its own future internal activity. It lifts those predictions up into increasingly abstract, latent spaces. This right here might be the exact secret to why human kids learn so incredibly fast.
All right, moving to Section 3, modeling hierarchical learning. It's time to actually test this theory.
To really prove out this biological intuition, the researchers used something called the Random Hierarchy Model, or RHM. Think of it as a simplified, synthetic, tree-like model. It's perfectly designed to capture how natural language and images are structured hierarchically. In this setup, you start with high-level abstract ideas at the very top, the root, and then through specific rules, you branch down step by step until you finally reach the visible data at the bottom, which we call the leaves.
Now, take a look at how the data flows in this hierarchical structure. This represents the punishing cost of traditional token-level learning. The data flows from the abstract root all the way down to the visible leaves at the bottom. If an AI model is only looking at those bottom-level tokens, the statistical signal it needs to actually learn the high-level concepts has to travel all the way back up the tree. And at every single step up, that signal gets diluted. It's incredibly inefficient.
But now compare that to a learn from your latent approach. Notice how the model isn't just fixated on those bottom leaves anymore? Instead, it's predicting targets horizontally, directly within the hidden layers of the tree itself. It's completely bypassing those noisy surface tokens and learning the structure level by level. It's a total paradigm shift.
Section 4. The efficiency breakthrough. Let's dig into the math.
Okay, this is the ultimate showdown presented in the research. On one side, we have token-level learning. Its data cost scales as m to the power of L plus 1. Here, L is the depth of the hierarchy. That means the amount of data you need grows exponentially the deeper and more complex the concepts get. But on the flip side, learning from latents scales at m cubed. Do you notice what's missing there? The L is gone. Completely gone.
The data cost becomes constant, entirely independent of how deep or complex the hierarchy is. That is an exponential breakthrough in efficiency.
So you're probably wondering, how do we actually pull this off in practice? The researchers outlined an algorithm they call iterative latent clustering. It basically works in 3 steps. First, it forms groups, or tuples, of data at the current level. Second, it estimates context vectors, which is really just a fancy way of saying it looks at the surrounding neighborhood of the data. And third, it clusters synonymous concepts together to construct the next level up. It literally solves the tree one level at a time.
And just to prove this isn't purely whiteboard math, the researchers actually built a neural network called the Stacked Latent Clustering Network. This network perfectly mirrors that algorithm we just walked through. It uses dedicated predictor and cluster of subnetworks, and amazingly, when they trained it, it perfectly hit that highly efficient M-cubed mathematical bound. What's even cooler is that it works using biologically plausible learning rules. It's literally mimicking how our own brains might operate.
Section 5. Towards Human-like AI. Let's ground this data in the real world.
So how does this math apply to the real-world architectures we're building today? Well, the paper examines a popular self-supervised algorithm known as Data 2Vec. In Data 2Vec, you have this really clever setup with a student network and a teacher network. The brilliant part here is that the student isn't trying to predict raw pixels or text. Nope, it is explicitly trained to predict the latent representations generated by the teacher network. It's implicitly performing that exact hierarchical latent prediction we've been talking about this whole time.
And here is the absolute mic drop moment of empirical proof. Normally, learning curves for something like Data 2Vec would be all over the place, totally dependent on the complexity of the data. But when the researchers rescaled the data requirements by that magic math formula, m cubed, all the learning curves perfectly collapsed onto a single predictable line. This proves the math works absolutely flawlessly in practice.
I really want you to take away this specific insight from the paper. Every level becomes as easy as the first token level step. By lifting the prediction target up into the latent space, so predicting concepts instead of pixels, the AI completely shatters that punishing token bottleneck. It just doesn't get exponentially harder to learn deeper concepts anymore. It's a massive leveling up.
They even peeked under the hood of the Data 2Vec algorithm as it trained. As you can see, the synonym clustering scores just shoot straight up. This means the AI's encoder is quite literally collapsing synonymous concepts together internally. It realizes, oh hey, these 2 different raw inputs actually mean the exact same abstract thing, exactly as the math predicted it would.
Which brings us to our final big picture thought. Right now, the AI models we use every day are slamming into massive, incredibly expensive data walls, mostly because they're obsessed with predicting the next token. But if mimicking the brain's predictive coding, learning from latents instead of tokens, is exponentially more efficient, could latent supervised models be the key to breaking our current AI scaling laws entirely? It's a huge question, and looking at this math, the answer just might be yes. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you next time.